Welcome back, guys. So, today, last week we left off around here. So, I believe we managed to get the switching working between processes and between the interrupt handler. So, right now, everything just works. So, let's just run it once. So we are switching between two processes. I guess this will be the first process, and after 10 time slice we move to the second process, and after 10 time slice we move to the third, and it just keep happening. And also the timer interrupt is handled because at every time slice we have a timer interrupt, and it is handled back and forth between the user process and the interrupt handler. So that part is also working. So we were good at this moment, at this point. So now let's just think about what we have to do from now on. So now that we have a proper switching, what we need is the actual syscalls, because the whole point of switching between user process and the interrupt handler is not that is mean EL0 to EL1 is not just about handling time interrupts. We also have to handle user level synchronous interrupts that we have defined. As you can see, EL0 sync entry, that's a different entry. Currently everything is handled here, which is the IAQ entry, but we have the EL0 sync entry, which would be a syscall, and we have already defined that part. It's just about checking what syscall number that we have invoked, which is in ARM. It's every specific number with the SVC as the instruction. I guess we just call SVC with a specific number, and that particular syscall has to be invoked in EL1. So when SVC is called, it will trigger an synchronous interrupt, I believe. So when we come into this handler, we just have to read from this register to find the proper number. And first of all, we need to confirm whether it is a syscall or not. So we check if it's a syscall based on this code. I guess I have streamed it previously about how to write this part. So if not, we just jump and say that it's not a syscall. If we are here, it should be a syscall or some sort of soft exception. But those cases are not implemented by us. So currently, if we reach here, it should be a syscall, most probably. But still, we have this check. And then we move the arguments, the possible arguments, into different registers. And we double check the actual number and move it into x0 and all other arguments as x1, x2, x3 and x4. So x0 will be the actual syscall number and all other arguments will be the actual arguments. So we have and then we call the syscall dispatcher. This is what we'll have to probably implement. So let's check that. We go here and we have it here. It's a pretty simple execution, as I said. If the first argument will be the syscall number and the rest will be the arguments, and I guess it's bounded I don't think syscalls can have dynamic arguments, and they are limited, I believe. I guess that's why I only have three arguments. Maybe I'll have to double check that. And then we call the function, and we just switch using a switch case and allocate the proper thing and return it back. And I guess I tried to initialize case 5, which is a malloc. So no, probably it's a map. So I'm just allocating a bit of memory and giving it back to the user space as an address. But this would be in virtual address, right? Yes. Then how come user process will be able to write to it? User process wouldn't be able to write to it. I think we'll have to add to user to kernel to user space mapping here, but we shouldn't do a lot of code inside sys handlers because it's an interrupt. To make it as small as possible so we don't get descheduled back inside a interrupt handler. Well, anyway, in my case it is not possible because if it's from EL0 to EL1, my interrupt handler won't switch the process back, because even if its time slice is already over. So let that be. I guess right now, let's just check syscall number for write in ARM. Maybe I should have just asked syscall number for write in what is that, in Linux, not ARM. Yeah, now currently it's just taking it from Linux for ARM architecture. So in that case, let's just check write syscall. ARM64, we would call instruction svz0 syscall number would be in W8 and return value will be in x0. It has a return value 2, it will be in x1. Okay. And how do we pass the arguments? For syscall, argument 1 will be x0, x1, x2, x3, so it's just straightforward. Okay. I think right now this is syscall. So this is the actual operation that is going to call the svc. But now let's just see Linux write syscall ABA. Linux write. So if we get it, how do we know the number that is associated with write syscall? That's what I want, so that I can use it in my code. So my kernel should be Linux ABI layer, so we don't have to worry about writing our own compiler. The normal ARM compiled executable should just run fine in my case. That way, that way we don't have to really do much work. Okay, I don't know. Maybe this syscall.h will have the numbers. Okay, yeah, the syscall numbers can be found here. So if we just check for write, I have 18 hits. Oh, fuck you. Where's the number? There must be some number. I guess let's check write Linux. I guess it's 2. I don't know. It says call number. So in x86 it's 1. What about ARM? Yes, that makes sense because as you can see, the syscall number should be passed to, what is it? Here it says W8. So this is fucking LLM is wrong. Oh, that's ARM EB. Okay, as per ARM EB, let's check ARM 64. Yes, okay, so LLM was able to figure that it's W8 properly. That's good. And I guess we also have to follow the same method. We should not come up with our own implementation. Yeah, let's just check. Let's just write down what we need and then we can think about it. If it's a syscall, as per the documentation for ARM64, we should have syscall number in W8 register and ret value 1 in X0 and ret val 2 in X1. Currently, do we return anything? I don't think we return anything. Yeah, currently there's nothing here for me to return. I think I'll have to fix my scheduler to return the out vals. Here, okay. What else should I have to fix? I'll have to fix my syscall dispatcher. I think I don't have to fix this part because I can do the meddling here and properly change the arguments and pass it specifically to my syscall dispatcher. But what I can do is that I need to update. Okay, so I do have it updated. So it is possible to have two return values. And maybe we'll have to check how two values are returned and what's the signature of it. But right now, let's just, if we assume it, then we'll have a big issues in future. So maybe we'll have to but what do you mean by X2? Let's just check what does that mean. Syscall taking input number through W8 and return values in X0 and X1 as per docs. How give me an example of an syscall that returns two outputs. Specific syscall is defined to return a second value. That's like, what is that second value? Okay, the classic example would be a pipe. How is that? Because it only has one return type. Okay, this makes lots of sense. Generally uses memory instead of X1 for X. So I believe we don't have to support that second argument. Well, if I write my kernel and if my syscall does not return the second output in x1, would that break any API for ARM compiled executable? Okay, so it does not matter. So everything else should be handled in the AB, the higher level. I think it's fine. I think we don't have to worry about it at all. But I don't know, because as per the documentation it says that there is a possible return value here. I don't know. Maybe we can use it, but I guess in general, compiled binaries don't use that, so it should be just fine. So we don't have to worry about that. Only thing we'll probably have to worry is that I don't think anything else is needed, because in our case, we do, once we switch the registry inputs to the specific values and we return the proper output in x0, it should be just fine. What else? Let's just write down all the to-do so we can keep track of things properly. To-do is just getting too much. Okay, so first of all, fix the sync handler to read the inputs syscall number from x8 w8 specifically. I guess it's first 32 bits are only used. Okay, that's fine. Fix the return address, return value in x0. Okay, those two things needs to be done. And let's check our handler. Handler. Yeah, we do already have one syscall and we are returning a virtual space address, so we need to fix that. And I've already added that fix here, so let's just add that for here too. Add user space map from kernel for syscall 5, map the virtual pages into the user process. This is what we need to do. And add the syscall for write. Okay, let's just start with this part, so it would be easy. This is called to read input from W8. We need to read from W8 let this check be as it is. And what the fuck am I doing? I'm moving x0 into x3, x1 into x4, I guess I'm just doing temporary allocations because I don't know. So x4 has the syscall number. This is the first argument, and I guess there could be up to 7 arguments. So I should also possibly handle up to at least 6 arguments. Okay. I need to at least handle up to 6 arguments. And the arguments should be in x0, x2, x1, x2, x3, 4. Because the actual compiled binary might just pass it in these arguments. So I cannot change anything here. Well, actually, if I just follow this step, and if my binary is going to set those values in these proper registers, I don't have to do anything here. I could just directly pass I could have 6 registers x0 x0, and I can pass x8 as x7 as my x7 or x8 as my syscall number. And actually, yes, x8 is already the syscall number. So I really don't have to do anything. Wait. 64 function call arguments, the registers, register order. Okay. So as per ABI, first 7 will already just be taken from that, and my x8 will have the syscall number. And I also have to pass that to if I want to pass 8th argument to the function, what happens? I guess if it starts from here, 3, 6, 7, 8. So this is the 8th argument, 8. And we only have 6, 3, 6, 7. Possibly 7. But 7th is not even documented here. So we only have to keep 6 as it is. Let's just keep 6 as it is. And in the 7th argument, let's just pass the 8th value and change the definition function signature. Yeah. I just need to confirm what the fuck is this, and then I can... Okay. This is to take the syscall number. take the lower 15 bits into x0. What does that mean? This will be stored here and then I'm moving it to x0. Okay. Okay, then I have to do this for what? x8. Because x8 is the W8 means last 32 bits, so I think this should be fine. This will be the actual place where we put the argument, that is the syscall, and we don't have to do anything. Rest will be the same. We don't have to move anything. Let it be as it is. No, we have to move one thing, that is move the syscall number into, we move the 8 and we move it into what? We move it into which register? x8, so we move it into x7 because we'll use 6 registers. We'll use until x6, and x7 will have the we'll have it, and we can just call the syscall dispatcher, and let's also just, the return value should already be in x0, so I think I don't even have to do anything here because the function should return it as x0. So that should also be good. Only thing I'll have to change now is the handler's interface. So syscall number won't be in the first one. So let's move that. Let's move till, let's just take this argument 1, argument 2, argument 3. And let's just copy this. Argument 4, argument 5, argument 6, argument 7, and this is call. It should be 4, and it's 5, and it's 6. We have 6 possible, and 7th, I don't know, so simply let's just keep 7th. And we can have the 8th one, which is the syscall number. That's it. Put syscall. Okay. That should be good. We have the all possible arguments, and depending on the syscall should handle whichever arguments it needs. So that doesn't matter. The rest of the arguments will just have probably empty values. That should be good. I think we managed to finish that part. Maybe we'll have to finish it inside the user. Let's just call the 5th syscall here. Where is it? It came in. I think I don't have any user processes. Yes, I think I didn't write any user process. Let's just add that. Mm, but it's a user level thing. So yeah, maybe at this point I'll have to start separating my user codes, because currently my user code is here, which is not good. It's simply just two processes, and they are already put inside the kernel memory range, and I'm just mapping the addresses into user space table and giving the illusion of it. I mean, in general, maybe first of all we need to give some exec or something, a syscall like that, that will just take a empty blob and convert that into actual memory model, or it will map things into the memory and actually load the process, something like that. Yeah, maybe we'll have to do that. Let's just finish a simple example and then we'll a simple syscall, make it work, and then we'll write the actual syscall that is going to load the syscall that will load a blob of data as executable into memory in ARM64. I guess that is the exec. Yeah, load the full ELF binary. So exec, we will take the blob blob, load it into memory, create separate table, page table for it, and what other requirements does it need? Get a task struct for it, and add it to scheduler queue. Is that how it works? What is the actual flow of loading a new executable? Yeah, because as you know, a kernel is simply just a layer, and the actual user's process is probably just a file system, and we have the init, and the kernel just executes init as its first function, and init will have its first PID1 or PID0, whatever it is, and everything else is a executable that is loaded into memory. So the kernel jumps into init and everything else is just blobs of executables that are loaded during runtime and has given a separate virtual space. Open the executable file. Okay, so there's lots of steps, and we create a fresh address space, new stack, okay, that's good. So at least we are somewhere close. And then we set the PC to ELF entry point. ELF, that is the ELF start underscore start. And then we also set up the stack, and we jump. I think there's lots of stuff left to do, because first of all, we need an entry. First of all, we need a user space. Only then we can enter into it. Currently, because I recently, I guess maybe 1 or 2 months ago, I learned that the entire Docker is just simply Linux namespaces and separate ch root. Because like, if you just know what is change root, you would know that you can create a mountable image, and you can create separate executables, separate directories inside actual file system, and you can jump into that file system using chroot, and that root will be the initial init, and it will be using the kernel, and it will only see whatever inside that file system. It's like a small Docker image, because Dockers are just separate file system and separate namespace. That's it. And I guess C groups, nothing much. I guess that's why people don't consider Docker as a security layer. Docker is probably just simple separation for file system. So in our case, currently there is no file system at all. There's only RAM. Yeah, there's only RAM and the actual kernel ELF. Nothing much. So first of all, we need to give it an actual file system to enter into, and keep a init inside it, which should, let's say, execute a shell. And then from inside that shell, we can think about loading binaries from the file system. So there's lots of extra step that already needs to be done before even we can start with this. So I don't think we can do those parts at this point. Maybe we can write it down inside, or we can have it in our mental model of what we are working towards. Because currently we still need a long time goal. That is, we need a init that the kernel should jump into. Before that, we need a file system. Even maybe like temporary RAM FS, even something like that. Let's just keep our temporary file system in the RAM and jump into it, like the actual OS booting process works. Because initially we do need a temporary file system, and then we load certain stuff, and then we jump into the actual file system. So we need a file system. Let it be be a temp RAM based file system, and then we put the init in that, and that would be the actual first process, and that is going to be running in background thread. No, that is, let's say in our case, it's just going to be bash. So it's going to run and it's going to fork every other process as child process. Your file system, that is temporary system, and that is a bash shell, because we can't implement the entire bash shell. Let's just maybe write a small bash shell that can at least only do cd, ls, and what else, and execute something, that is the execv. That's all, with cd, ls, and exec. And we can put the actual user process inside this file system and load it and run it using the shell. Okay, so let's say we run it. What happens then? We run it. Yeah, we run it. That's it. But then probably we'll have to try it by running 2 processes at a time to see how scheduling works. What else? Before that, at least we have to finish maybe 20 syscalls, because without that there'll be lots of things, because we won't even be able to click Control C, because once we enter into that bash shell, everything is inside user space. So if we want to achieve something, we have to handle a certain level of syscalls. Because even that bash shell, might need to handle the actual Control C or the syscalls, what is that, SIG handlers. Okay, this is just high level picture of what we need to do, and based on that we can fix things, because right now we have fixed these 2 parts already, because it was pretty simple. Because if our user process is going to send those arguments in those proper order, we don't really have to do anything in the handler. We just have to improve our syscall dispatcher signature, and that was pretty good. And probably now we'll have to do these 2 parts. But I'm wondering, okay, yeah, let's just add some syscalls, add a few more important syscalls, and then we need a file system. I guess we can think about it right now. And then we need a file system, and the file system should have the initial init b, which would be our first process, and kernel should execute this as the first process. Okay, that way we'll have an actual differentiation between where our user code lies and where our RAM is, because okay, even if I'm going to run something, that needs to be inside the RAM. Anyway, I have to load it, so I have to implement execv. Exec. Put the usual actual user process inside the file system, or it is usual. I think right now we just start with implementing few more syscalls. Once we have enough syscalls, then we can start writing the file system layer and then put the user process inside the file system and ask kernel to start from there, because right now we have a first user entry. We just change that it to jump into this form of process, which would be the init d in our case. And then inside that init d we would have to actually implement the bash commands. At least we need 3 commands, and those commands are going to, and one of it is going to actually call a syscall that's going to load the things. Okay, but let's just start by implementing these, because I guess this is not going to happen anytime soon. This is just future theories. Right now we need write, exec, maybe also probably read, write, and also probably close. Read, write, close, and exec. Let's just write these function calls. What about mmap? Do we need mmap? No. Mmap is just going to get some more space, and user space can use that. I don't know. Maybe I should finish mmap first. I think that's not needed, because even if I finish that, I'm not going to get anything. At least if I finish the write, syscall, close, and exec, I would get some sort of improvement in the overall. And in general, because both my user process and the kernel is in the same RAM, I mean at least in the same space, currently I don't really need to allocate anything. Whatever I allocate inside user space should already be accessible by the kernel space. Write, read, close, and exec. Okay, these are the things that we are going to allocate now. Okay, let's finish write then. What is the write handler number? Or is nr write? I think we should be finding that in these things. TBL. Okay, we also have ARM. We have ARM 64. Okay. Okay, it's here. And this is ASM generic, uni standard. Read is 64, write is 65. What does ASM generic mean? Shouldn't I be checking it? This is some old. Let's just check the latest. Okay. In master, let's get into include. And inside include, let's go into API. ASM generic. Uni standard. File contains a syscall numbers based on the layout of x64 architecture. I mean, is it for x86-64 alone? What about other architectures? If I had an ARM architecture, I would just simply. If I have a Linux, I could do that because I could just compile a simple printf and put ltrace or strace and see all the syscalls and see what was the syscall number they are using. Currently, because I'm fucking using a Mac, I can't do that. Maybe I can. How can move? I just need the numbers, man. I just need the proper numbers. I think if I go into inside Arch and I go into Arch ARM 64 and everything looks fucking different now. Let's see. Arch entry. It's entry syscalls. What? Tools? Scripts. Syscall. There's no fucking scripts. What the fuck? This column is for all more recently added architectures. Basic principle: no duplication of functionality should be added. Use lseek when llseek is present. New architecture should use this file and implement the less future-full calls in the user space. Okay, whatever. Let's fucking read. Come on, write. Okay, right. Okay, it is 64. Okay, let's just put read should be 63. Right should be 64. And read, write, maybe close. Or exit. Exit is 93. Close. Close is 57. Let's double check, it's 57, right? Okay. And we need close and exec v is 221. Exec cv is 221 and mmap 222. Maybe we need also bark. brk is 214. Maybe implementing these syscalls should be enough for my setup. Is implementing this syscall enough for this simple kernel setup? Let's see. Okay, we need lots of stuff. We need okay, so shell needs open, but I am going to implement the shell, so I don't know if we need all these. You have a file system layer, file descriptors per process, inode, directory structure, superblock, inode table, directory entries. I guess we do have these two. Maybe a little bit of exception handling. We have page allocator, page fault handler. Okay, if we access a memory location that is not handled, we also need page fault handler. Okay, maybe we can write that. Okay, we need these two. For process level, we need these syscalls. We need fork, exec, exit, and wait. Okay, we also need wait. And for file level, we need open, read, write, close. And okay, because everything inside the kernel is just a file, so everything in Linux is just a file. We can just write the file operations, so we will get a baseline of what we need. I think this is what we need to write. This is what we need. We'll have to keep this in as a bigger picture. Maybe let's just put it inside a doc. Then any fucking doc. Things to check.md, readme.md. What is this? Okay, let's just delete this and bring this here. This is what we need. Oh, fuck you. Oh, fucking. I can't paste without leaving that indentation. Fuck. Shit. Okay. I think we have this. I think in general in core layer we do have everything. We have the EL1 to EL2 switch. We do have an option to create page tables per process. We have context switching working fine. We have exception handling to a certain extent. In terms of memory allocator, in terms of memory, we need a page allocator, we need a page fault handler. I don't know what this means. I'll double check this. Check this again. We need two function calls to syscalls, that is mmap and bark. We'll add that. We'll add these two today, or at least tomorrow. And then let's see, we need these syscalls for process. Fork and clone. Let's just add fork and clone. We need these syscalls. Only after that we can even think about the file system layer too. Right now, let's just implement all the syscalls that are potentially needed, and then we can think about the higher levels. Because I don't think right now we will be able to get into those stuff, because if we try to get into this, we'll just be stuck, and or we'll be trying to get around things, which is not good. We need a baseline. I think this will be a good baseline. Because in general, it's just syscalls. If we have these syscalls, we can use these syscalls to write the upper abstraction layer, which will be the file system, and we can write the process level abstraction, and we can also write the memory level abstraction, because these things are going to be written from the user space, because everything as soon as the kernel jumps into the init, everything is happening in the user level. So only if we have these stuff in the user level, we can even do something meaningful. These two are not in user level, but we do have these parts. Let's just see. Explain why we need this in a picture of kernel flow, and explain with an example to see the flow, and how compare this with minimal Linux API. Let's just understand the theory first of all. Without that, we won't be able to get anywhere. What a kernel actually does: protect memory, schedule execution, and provide controlled access to hardware. Okay, fuck that. Okay, so this is the actual flow. We start, the kernel starts, the kernel loads. Kernel loads as in we load ourselves into the RAM, and we put ourselves inside the virtual kernel space, and then we jump into the file system in it, and there the shell runs and we do whatever shit we want to do, and the process exits. This is like a high level overview. There's lots of shit going on. Why do we need exception? We need exception because syscalls and interrupts, because in general if we just want to do a syscall, that means we are calling svc0, which is an interrupt, and that interrupt needs to be handled, which in our case we have the what do we have? We have the isync handler that will do syscall dispatching. Okay. Without syscall and time interrupts, nothing can work. We have everything. We have this time interrupts too. Scheduling. Okay. And what is EL to EL1 switch? We prepare, if kernel prepares a user stack and prepares a register and set the ESPR, and we hear it and we get into user process. This part is also already done. We have the switching working between EL0 and EL1. Okay, context switch, in that sense it would be switching between user process. This is switching between this is switching between interrupt handler and the user process. This is switching between user process alone. Oh, fuck you. We have a scheduler. We have a round robin scheduler. That can switch EL0 processes based on time slice. Okay, so that should also be good. What else? And we have a helper that can create, we have a helper that can create user page table, and we can use this to switch between processes and have the virtual separation. Okay, that is good. Now, why a page allocator? I think that's why I try to initialize. Everything needs memory, because from user space we need memory, and to do that we need a page allocator, and we have a page allocator. We have a page allocator, and user space took page map helper. Okay, this is what we don't have. If a process tries to access something that is not valid, should we kill the process, or should we allocate it and send it back? We need a handler that can decide whether to allocate or say this is wrong and kill the process. This is, we definitely need this. And we need bug, so to implement user malloc, we need vrk. I think this is optional. Well, let's just keep it optional, then we don't have to implement things that are not needed. And from user space we need this, because whenever we try to run some executable, we have to load it into memory, do a lot of shit, and fork, duplicate file descriptors, and new process text. Let's just write some notes for what everything does. It has to copy the address space from the ELF, or no, from ELF into address space. Address space, or copy data from ELF into a new address space. And duplicate existing file descriptors. Create a new process duct, which should be in our case task struct. Okay, what is clone? I think clone and fork is going to do the same fucking thing. I think fork will return back to PID, but clone won't, maybe something like that. Replaces memory with a new okay. This is the key that we need to implement, because this is the biggest step that is missing in our setup, because we need this to actually take an executable and do all these steps, because right now our kernel, we have a step where we init a task, we take a task and we do all the initialization ourselves, because we set things up, we say there's a entry function, stuff like that. But what we have to do is that almost everything will be already inside the ELF. We need to map it into user space, and from that memory locations we need to design these stuff. And this is the user process table I was talking about. Okay, this is still not dynamic. Oh, fuck it. We'll have to do that too. And if you exit, just has to free things. Free whatever we created, nothing much. Weights. Do we need weights? Shell can't know without this, okay. Okay, we need this too. And then file is just simply file system, operation is just open, write and close. This is just by default important, so we don't need special explanations for this. Full flow would be we type ls and we call read, because we need to read the file. Okay, this will be an interesting. So from the user space we type, let's say, ls, and we press enter. First syscall would be to read that file, because we read certain buffer. So we call the syscall, we create an exception, we get into EL1, we file read and we return, and the shell forks. At this point, this buffer would have this entire ls ELF, and then we call fork. Now the fork is going to allocate new task, copy page tables for this, because we have a specific page table for this particular process, and we duplicate FD if there is anything, and we schedule child. That would just mean we schedule this as the current executable that needs to be executed. And inside that, now we call exec ls. Why? Because we have already read that into a buffer. Don't know why the fuck did we read it into a buffer. I don't know. Oh, maybe this operation is to check what this is, because just because we typed ls, that does not mean our kernel would know what ls is, because it's just an interface, because we are inside a bash. So we read from the standard input this ls and we fork, and here we inside we call the ls, and this is what is going to open that file, read the lf, memory allocate it, map the segments and set up the stack, and return back to EL0. At this point we would have set the ELR EL1 with the address within the ls underscore start underscore ls, no, underscore start, that is within ls. And ls runs, ls can do whatever it wants to do. and probably it might want to call writes, so we would need these things. Parent as in the shell has to wait. Okay, we don't need this big. Let's just fix this flow. This flow seems just fine, and this flow seems interesting. We call ls. Let's just write the flow here. We call ls, and so syscall has to read the syscall read is called to read the input from standard in into a buffer, and then we call fork. This will allocate new tables, and it will allocate new tables and a new task struct in general, and then we call exec cve, which will load the elf and all memory related to that process, and run it. During execution, that process might call more syscalls, like read, write. Mostly it's going to be read and write. Let's assume that. And then we will probably have to exit the process. Also we need wait, because the shell is waiting somewhere for the child process to finish. I think that's it. In general, this is the flow that we want to first finish. For that, we'll need all these. This is the flow that we are going to finish. Okay. Okay. My data looks good. Okay, so we need the syscall entry, we have the syscall dispatch, we have switching, we have round robin scheduling, we have per process page table. We need to add these syscalls. We need this. We also need page fault handler, because we might need to allocate new page tables while we are inside the user process. Okay, let's just start implementing this memory things, and then, or maybe we'll start implementing this. Yeah, we'll start implementing the file operations, because that does not need any other requirement. I think so. Yeah. Okay. Yeah, today we just because we were done with a bigger milestone currently, so let's just start with today. We just started with getting an idea of what exactly needs to be done from now on, because we need the bigger picture of what we are working into, and I believe this structure gives us the good idea of what needs to be executed and what needs to be implemented. And if we can get all these working, maybe in upcoming weeks we should get a small working kernel. Let's see. Okay, thank you guys. I'll see you tomorrow. Bye bye.